Okay, so we're gonna come back and talk about two new circuits, our C circuits, and then we'll come back and talk about our L circuits. And we'll see a lot of parallels between these two. But let's start with RC circuits. So basically, a simple series RC circuit, if you want to charge your capacitor, so we're going to start with an uncharged capacitor, is basically you're going to hook up a battery, a resistor, and a capacitor, and you'll close the switch at t equals 0. At t equals 0, there's not any potential, there's no charge built up, so there's no potential across the capacitor. What's going to end up happening is that initially charges are simply going to start moving around the circuit, and so at t equals 0, your capacitor acts like a wire. And current starts to flow, and that of course starts to charge the capacitor. So if we think about what's going on at any time after that, then when we use our loop rule, and let's say we simply start here, and I know that current's going to be flowing this way around my circuit because of the way my battery is oriented. If I start here, I'm going to have an increase across the battery, a decrease across my resistor because I'm going in the direction of the current, and a decrease across my capacitor because this will be the positively charged plate, this will be the negatively charged plate, so I'm going from positive to negative across the capacitor, so that'll be a decrease. So using my loop rule, says this is what I'm going to end up getting. And I know that I can talk about the current or the voltage across my resistor using Ohm's law, V equals IR, and I could talk about the voltage across my capacitor by using my fundamental equation for capacitors. So this is just Q equals CV, where all I've done is solve for V. And now what I'm going to do with this is basically take a derivative of the equation. So I'm going to take the derivative of this equation with respect to time. Well, that's just the voltage of the battery. That doesn't change with respect to time. So that term becomes 0. di dt, there's that. The resistance, again, that doesn't change with time. That's held fixed for my resistor. Similarly, when I look at this next term, well, again, the capacitance, that doesn't change either. So I'm just going to pull out a 1 over c and be left with dq dt. And so here's what I get when I take the derivative of this equation. And so what you'll notice is I can rearrange this. So I get di dt, right, bringing this over the other side, dividing the r over, is going to be negative 1 over rc times dq dt. And dq dt, right, the time rate of change of my charge is just the current. So this expression dq dt is just equal to I. So what I get is di dt is equal to negative I over RC. And this is just a simple differential equation. Unfortunately, this one's basic enough that we know how to deal with it. So the easiest way to deal with it is to now just get my like terms, so all the I stuff on the left, everything else over on the right. And so you notice I get di over I over here equals negative dt over RC, and so now I need to integrate. I'm going to integrate the left-hand side of the equation from some initial current to the current at some later time, which means the right-hand side I'm going to integrate from 0 to t. And again, the 1 over rc and the minus sign, those are all just constants. I pull them out, so this integral really is just t evaluated at my endpoints. So this just becomes negative t over rc on the right. And then on the left, well, I know that the antiderivative of dx over x is the natural log of x. And so this is just going to be, when I take the antiderivative of this, is just going to be the natural log of I, and when I evaluate it at my endpoints, again using the property of logarithms, I can write the expression this way. So the natural log of the current at any point in time over the initial current. So I naught is just the current at t equals 0. And so now I'm just going to solve this for I to get my current as a function of time. So the first thing I need to do is get this, to get I out of the natural logarithm, and I know that the inverse of the natural logarithm is the exponential function. So I'm going to take e to the power of everything over here, that's going to give me I over I naught, equals, well, when I take e to the power of everything over here, it gives me e to the minus t over rc. And so now it's a simple step of getting the current as a function of time. That's just going to equal the current at t equals 0 times this expression e to the minus t over RC. So here is the functional form for the current at any time once I start charging my capacitor. So one of the things that I obviously need to deal with, or would like to deal with, is this I naught. So what can I do with the I naught? Well, before we worry about the I naught, let's come back and think about what's going on in here. So one is I know I've got the natural exponent, e, right, to the minus t over RC. So one of the things is I'm taking t and dividing it by this expression RC. Well, I know t is in terms of time, and I know that I'm plugging just a number, something that's unitless, into this exponential function. So the only thing that makes sense is if RC happens to also have units of time. And sure enough, you can prove to yourself by doing dimensional analysis that it does. And so R times C is just known as the capacitive time constant. And so I can rewrite this expression if I want to in terms of I naught times e to the minus t over tau. So what is it that that time constant's trying to tell me? Well, basically it's the time for 63.2% of the final charge to have accumulated on the capacitor. So after one time constant's worth of time, so you close the switch at t equals 0, after one time constant, 63.2% of the final charge is now sitting on the capacitor. So in terms of what that looks like graphically, well, what that means is that what's going on with the current is, again, we know that initially it acted like a wire. And as I build up more and more charge, this e to the minus t over RC, well, again, as I make t larger, e to the minus a large number effectively becomes 0. So you see that this drops off as time increases. And so at t equals 0, the current across my resistor is equal to the voltage over my battery divided by the resistance of the resistor. At one time constant, 63.2% of the charge is now on my plates, but the current has dropped to 36.8% of its initial value. And so it's fallen by 63.2%. And then you notice that once you basically get past about 5 time constants, effectively there is no current flowing through the circuit. So as t approaches infinity, which from a practical standpoint really just means that you've got in excess of 5 time constants worth of time, there's no current remaining flowing through your circuit. Alright, so to deal with that I naught, and again just sort of deal with it in terms of the equations, well, we know that at t equals 0, our capacitor acts like a wire. So if I think about the loop rule here, right, so I close it at t equals 0, this is basically what my circuit looks like. The capacitor looks like a wire, the switch is now closed, and so my loop rule in this case tells me that, well, I'm going to increase across the battery, I'm going to drop across the resistor, and that's all I've got. So it's easy enough to plug in that, well, since this is t equals 0, the current across this is just my current at 0 I naught times the resistor. And so solving this for I naught gives me, sure enough, exactly what we were talking about on the previous screen, that V over R is what I naught has to be equal to. So again, this V here, again, this isn't a changing V. This is the capital V that corresponds to the voltage of the battery. The little v's are telling us how my voltage is changing across the resistor and across the capacitor. But this is just the voltage of the battery, and that's constant. So I can come back and plug this into my equation. So what I get is basically that the current as a function of time is equal to the voltage of the battery divided by the resistance of the resistor. That's the initial current in the circuit times my e to the minus t over RC. So if I want to think about the voltage across the capacitor as it's charging, well, now again I'm back to the expression where I do need to include the capacitor because I want it at some time where it does have charge. And if I solve this for VC, what I see is it's the voltage of the battery minus the voltage across the resistor. And the voltage across the resistor is just going to be my current, again, this expression right here, V over R times e to the minus t over RC, times R. So obviously the R's cancel out. I can factor out the V, and this gives me the voltage across the capacitor. So there's a couple things that I have to be aware of here. One is I can talk about the voltage of the battery. That doesn't change. That's fixed. I can talk about the voltage across the resistor, and that's going to drop because the current is dropping in the circuit. And Ohm's law tells me that the voltage across the resistor is equal to I times R. And then there's the voltage across the capacitor, which is increasing as more and more charge gets put on the capacitor plates. So we have to be careful in talking about what element, or in talking about the voltage. We've got to make sure that we're precise in terms of talking about what element we care about the voltage for. And again, at one time constant, notice that the voltage of the resistor has fallen and the voltage of the capacitor has grown, so that this is now the 63.8% and this is dropped to 63.8%, and so that's what those values are. Okay? So this is what happens when we charge. Again, at t equals 0, there's no voltage across the capacitor because there's no charge on the plates yet. Vc, the voltage across the capacitor, is 63.2% of its final value after one time constant. And as t approaches infinity, the voltage across the capacitor is now equal to the voltage of the battery. So for our simple series RC circuit, I'm going to end up with basically the capacitor acting like a second battery that's trying to drive current in the other direction. So there's no current left, all the current is dissipated away, and I have a capacitor that's charged up just as much, or that's charged up so that its voltage is the same as what the battery is. Okay, so just to summarize, if we're charging a capacitor, we said basically we know that as the charging progresses, the voltage of the battery is going to stay the same. The current's going to decrease, so the voltage across the resistor will drop. The charge on the capacitor is going to increase, so the voltage across the capacitor also increases. And again, here's the same graph. If this is our expression for the current, and again we said, hey, I can solve for the expression of the voltage across the capacitor. Well, the charge across the capacitor is just going to be C times the voltage. So this gives me the charge on the capacitor as a function of time. And again, where I'm thinking about this in terms of charge, so that's the charge is the red plot here. The black one is the current. Right? So the current as I'm charging is dropping. The charge on my plates as I'm charging is obviously increasing up to some value Q max, which is equal to the capacitance times the voltage of the battery. And so at t equals 0, no charge on the capacitor, no voltage across the capacitor, and the current in the circuit is equal to the voltage of the battery divided by R. As t approaches infinity, on the other hand, now my capacitor is fully charged, so it's equal to C times V. The voltage across the capacitor is equal to the voltage of the battery, and there's no current left in the circuit. So this is what's going on when I'm charging a capacitor. For discharging a capacitor, again, you could walk through the same process. Your book does a decent enough job of it that I'm really just going to sort of summarize here. But basically, when I'm discharging, I take the battery off. Now I have my charged capacitor that's initially at has some potential across at V0, and then I'm going to close my switch at t equals 0, so all I've got is the capacitor and the resistor, and so my loop rule basically tells me that the voltage across my capacitor has got to be equal to the voltage across my resistor. So in this case, all of my values are falling off exponentially. the voltage of the capacitor, the voltage of the resistor, the charge, the current, they're all dropping exponentially. So they all follow the same decay curve when I'm discharging. Again, this maximum point corresponds to, well, it's either the maximum voltage across your capacitor when you close the switch, it's the maximum charge on your capacitor when you close the switch, or it's the maximum current that occurs at the instant you close the switch. So here's the functional form, and all we're really sort of changing is just what the maximum value is, depending on whether you want to talk about the voltage of the capacitor, the charge across the capacitor, or the current. And again, you can see that the voltage across the resistor and the voltage across the capacitor, if we're discharging, are exactly the same. Take this, multiply it by R, all it does is cancel that out, and I get the same expression for the voltage across the resistor as the voltage across the capacitor. So these are the two scenarios that we'll deal with RC circuits, is a charging capacitor and then a discharging capacitor.